Now let's look at some refracted and reflected waves on strings. I made two sets of strings. One is a light rope tied to a very long metal spring. The other is made of a light rope. In order to have similar texture for the entire rope, I braided 3 of these together to form a thicker rope on the left side. The first demonstration is for a downward pulse coming in on the right side in the metal spring. The video you see here is the top view. I placed black poster boards on the floor so you can see the strings clearly. Since it's top view, when I say downward pulse, I mean the pulse goes horizontally toward the bottom of the screen. The pulse is horizontal, so we don't have to worry about how gravity affects the waves. This is the incident wave traveling to the left. Then half of the wave pulse is in the lighter string. As you can see, the refracted wave in the light string has almost the same amplitude as the incident wave. Although the refracted wave in the lighter string carries less energy than the incident wave in the metal spring, they can still have similar amplitudes. We can explain this qualitatively using simple harmonic motion. We know that the total mechanical energy of a simple harmonic oscillator is 1/2 k times amplitude squared. For less energy, if the force constant k is smaller, we can still have similar amplitudes. Now we can see that the refracted wave in the lighter string is wider than the incident wave, because the wavelength is longer for faster wave speed in the lighter string. On the right side, you have the reflected wave traveling back to the right. Because the wave is reflected off of a lighter string, it is like the wave is reflected off of a free end. Therefore, the downward incident hump is reflected as a downward hump. The next one is for a downward pulse coming in on the left side in the braided rope. This is the incident wave traveling to the right. Then part of the wave pulse enters the light string. Now you can see that the refracted wave in the light string also has almost the same amplitude as the incident pulse. On the braided rope, you have the reflected wave traveling to the left. Again, because the wave reflects off of a lighter string, it is like reflecting off of a free end. The downward incident hump is reflected as a downward hump. For the next demo, a downward pulse comes in on the left side in the light string. This is the incident wave coming from the left. Now most of the wave pulse has refracted into the metal spring. You can also see that the reflected wave on the light string is an upward hump. Because the wave reflects off of a heavier string, it is like reflecting off of a fixed end. The downward incident pulse is reflected as an upward pulse. On the light string side, we can see that the wave is wider because wavelength is longer in the fast wave speed lighter string. In the last demo, a downward pulse comes in on the right side in the light string. This is the incident wave traveling to the left. Here, half of the wave pulse has propagated into the braided string. Now on the lighter string side, you can see that the reflected wave it has an upward hump. Because the wave is reflected off of a heavier string, the downward incident hump is reflected as an upward hump.